Hello everyone. Let me start by explaining my title. What do I mean by cooperative evolution? Throughout the history of computing, there was a repeating pattern when systems became too complex to handle. Engineers came up with reusable building blocks and new and better abstraction layers. And in addition to making systems easier to understand and design, this had an additional advantage. It created a lot of opportunity to share the development costs and efforts both on the software and hardware levels. And this created a lot of cooperation even in a highly competitive market. And this basic pattern is repeated with the Ethereum ecosystem too, and I'm not just talking about the blockchain, but also the auxiliary services, including, of course, Swarm. And these should be building blocks for the next generation of decentralized applications, and this is a great idea, and there are lots of even better ideas to make this platform even more performant and useful. But also, the peer-to-peer client designs are already very complex. We have many protocols, many clients, and it seems like we are going to have many more protocols. So maybe it would be time to try to find new abstraction layers and new reusable building blocks of protocol design. So in this talk, I would like to explore the potential use cases for employing virtualization techniques on the individual node level, both in order to improve existing protocol and client designs, and also for moving toward a more general universal protocol, which would be based on a remote code execution. And then finally, I would also like to propose a virtual machine architecture, which I believe would be suitable for applying applications on the individual node level, and also for verifying remote code execution. Now let's take a look at the internal structure of an LES server as an example. And in the yellow boxes, I showed those parts which I believe could instantly benefit from being virtualized. And the green boxes are those which should provide some kind of backend interface for these virtualized modules. And I will quickly explain what this means. So there are already multiple reasons for why we would want to virtualize parts of a client. And I think the most important one, which I already mentioned, is remote code execution. So in the light client protocol, in the LES protocol, we can make an extension. We can make a new special type of request that would allow clients to execute some virtual machine code remotely on the server side, of course in a resource-limited environment, and access all the green boxes, which could provide everything that LES can provide for its clients right now. It could provide access to the chain database, state database, the current state of the blockchain, and even the transaction pool. And this could yield multiple advantages. First of all, it would be possible to collect all kinds of data in one request reply exchange. And also by giving access to the peer-to-peer layer and making it possible to forward requests to other clients. So we could implement a flexible and easy to develop a request forwarding scheme, which would be essential for sharding light clients. But there are other potential reasons why we would want to virtualize certain modules. For example, for extendability. And for that, a good example is the client connection logic, which decides which clients to accept and how much bandwidth to assign to them. And while there's a simple default logic for this in the current LES server design, if we could make this module replaceable or extendable, then LES server operators could start experimenting with all kinds of different payment schemes or prioritization methods, and these could be developed completely independently from the actual LES server design. And also there's a third potential advantage of virtualizing things, and that's the possibility to run an on-chain interactive validation. And in case of LES, the chain indexers would be a good candidate for this, because so these are producing the canonical hash trie and the Bloom filter trie, which I won't go into details, but these are helper data structures to increase light client performance. And right now, the root hashes of these tries are hard-coded into the Go Ethereum light client, which is not a really nice solution. But if we could canonize these root hashes on the chain, every new version of it, then we could implement a trustless checkpoint syncing for the light client. And now that we have talked about remote execution, we can take this idea one step forward, and we can realize that once we have the remote execution request, that's basically all we need. We can access everything else through the backend interfaces, and we can apply this approach to all kinds of protocols. So in the end, we can create a universal peer-to-peer protocol which accesses all the application-specific interesting functionality through backend interfaces. So well, it's not a fundamental change because we just moved some functionality to another level, but still we could have the advantages of increased flexibility in every protocol. For example, it would be possible to run a complex search on a big data structure in Swarm by just being connected to a few Swarm nodes. So even a light client could easily do this by hiring other nodes to do the data processing. Of course, if we want to make this thing really general purpose, then we have to think about verification of the execution too, because some operations can be directly verified on the client side with Merkle proofs and stuff, but some of them cannot. So there should be some mechanism to verify what the hired nodes are actually calculating. And I will go into the details later, but this is what the execution logger is for, which collects necessary information to replay certain parts of calculations. And once we have a general purpose remote execution in our protocols, we can do all kinds of things which are needed in a decentralized computing environment. We can process existing data structures with deterministic stateless calculations, and we can also observe and even participate in consensus protocols with higher nodes, both on public chains and state channels. So implementing hired shard observers would be really useful for sharding light clients. And since state channels are sometimes even harder to observe because interested parties would have to watch for their own parts of the state, it's even more important for light clients to hire someone who will do verification for them. It would probably even be possible to hire nodes to run a state channel. So light clients could have their own state channel for their own purpose too. Now let me also talk about the virtual machine design that I think would be suitable for using at the protocol level. And at the very heart of it, it's a really, really simple architecture. It's based on units, independent and deterministic units, which are only communicating with each other through message channels. And channels are also simple. Every channel has an owner unit, owned by a single unit, and the only one which can write messages to it sequentially. And units can also hold references to other channels. A channel reference is points to a specific message in the message chain of a channel, either an already existing one or a yet unwritten one, future message. And the messages themselves can also hold both binary data and references to channels and even to units. And units are constructed using prototypes which can contain already pre-compiled, even maybe JIT compiled WebAssembly code. I think it's obvious to use WebAssembly for this purpose. And also some I/O port definitions. And the actual instances would of course also have some internal state, some memory, whether they are runnable or waiting on an input channel. And the construction of the units themselves would be an event loop design so that they could wait for an input channel for a message to arrive, and when it arrives, do some processing, send some output messages, and wait for an input message again. And I repeat that it should be completely deterministic, so it's only possible to wait on single input channels. Of course, building a fixed topology of deterministic state machines doesn't do everything for us. So there's also a possibility to build modifiable networks and non-deterministic networks, and that's what system services can provide for us. And system channels, which are just general purpose channels, but all units have a pair of system channels through the system services. And these services can create new output channels for modules, can even give new instances of the system channels to modules, and also create new child unit instances based on prototypes, which the creator unit can wire its own channels to. And since we are still completely deterministic and not communicating with the outside world, in order to make this thing really useful and do something interesting, we can provide it with some system-defined units, and these units can do all kinds of time-dependent behavior, like channel multiplexing or timestamping, or implementing an alarm clock that sends a message on a channel at a desired time. Systems could also provide a random generator. And another thing that the system units can provide is the backend interfaces, the green boxes in the previous drawings, which can provide access to an Ethereum chain and state database if this is an Ethereum full node, or a swarm database if we're talking about a swarm node, and also provide an interface to talk to other clients. And besides constructing the network, the system channel has another very important function, which is scheduling. So whenever a unit goes into a waiting state, it automatically sends a schedule message to the system channel, including its own reference and the reference to the channel it's waiting on. And when the system service receives this message, that's when it actually schedules it for execution. Why is this important? It's interesting because we don't necessarily have to connect the system channel directly to the system services. It's also possible to connect it to intermediate units, which I call control units. They are just general purpose units. It's just their function that makes them special. And if these units can somehow process, limit, filter, modify the system channel messages, then it's possible to provide all kinds of different virtualized environments inside the virtualized environment, and this can create. So this makes it possible to limit what the child network can do, or log what the child network does, or even control the execution of child units. So here's an example drawing of a load balancer, which what it does is when it receives the schedule messages from its children, it multiplexes them to its own system channel in a way that guarantees that both of the units can have their necessary CPU time, maybe even limit the CPU time they receive. So it's also possible to implement lazy execution of these networks by controlling system messages. I already mentioned the execution logger, which is necessary for verification, and this is also implementable in this way. And it's also these control units can also limit what system unit instances the child network can create. For example, it can disable creating non-deterministic units if necessary, and it can even add a wrapper to system units. So for this, a good example again is the LES remote code execution, because when the application code receives the state access backend interface, it can be wrapped into a wrapper that collects all the Merkle proofs necessary for proving the operation on the client side, so the application code doesn't need to care about this. Now it's also possible to do even more modification of child unit behavior by even pre-processing the actual code of the child units. And so far I have talked about applications where we are modifying the capabilities of the virtualized environment, but these control units can also be used for creating the same virtual environment under different actual physical environments. So to go back to LES examples again, it's possible in a full node, it's possible for an application code to use the state and chain backend interface directly. On a traditional LES client, it's possible to use a simulated backend that uses LES requests to serve the backend requests. And in the remote execution setup, it's possible to use the before mentioned Merkle proof collector wrapper on the server side, and then when the proofs are returned on the client side, use a Merkle proof verifier wrapper, which could, and all of these could use the same application code everywhere, which provides us with a great amount of code portability. And finally, I would also like to talk a little bit about the verification methods that are possible with this protocol. And the heart of this is the execution logger, which I already mentioned multiple times. What it does is really simple. It regularly collects state snapshots of its child subnetwork. So it tree-hashes the internal states of its child units, and also collects message logs since the last snapshot. And luckily, this doesn't have to include those messages that are internal into the child network and coming from deterministic units. So in practical applications, this means most of the messages, but still this information is enough to reconstruct and rerun any piece of calculation on another machine. So whenever there's also the execution logger has another function. It retains these logs for a limited amount of time, and by connecting to the peer-to-peer layer, it serves queries to these logs to anyone in that given time period in order to prove correct execution. So whenever there's a disputed result, it's possible to request logs, and either we receive logs which could prove which execution was incorrect, or not receive anything, in which case we can be fairly sure that the node was trying to cheat. And of course, it's an interesting question. How do we detect when something has to be disputed? And it depends on the application. So if we are running deterministic calculations, then and if we want to be sure about the results, we can hire multiple nodes to perform the same calculation, and if the results don't match, then we can start going into the details and requesting logs and seeing what went wrong and where. But there are other applications. So I talked about hiring nodes for doing verification jobs, verifying other remote executors, verifying consensus chain execution. And so for these these processes are usually not deterministic, because they are connected to multiple other nodes and doing requests and stuff. So what we can do here is we can do a so-called weak verification, which is based on random sampling, and so not caring about whether we have reasonable grounds to suspect that someone is cheating, just randomly sometimes requesting pieces of calculation to verify. And of course, this doesn't guarantee absolute correct execution, but when we are just talking about a verification job, we don't really want to verify the results most of the time, because the results are most of the time is that everything is correct. So we just want to ensure that clients are not taking so hired nodes are not taking the easy way and not doing the verification and just hope that everything will be all right. So in the use cases when we are only worried about frequent and systematic cheating, then random sampling is also can be a good way, and it has lower overhead because there's no redundant execution. And we can hire multiple verifier nodes, and the verification routines can also run inside an execution logger. So all these verifier nodes can watching each other as they watch each other. So in the end, if we have enough verifier nodes, we can be fairly sure that at least most of them are doing their job and detect if one of them is not. And finally, this is optional, but if we want even more security, then we can add an interactive validation process as a final threat against trying to cheat. So interactive validations are expensive and very slow, so I believe these are not enough for ensuring that no one will ever try to cheat in themselves, but they are very good as a threat for being punished if a hired node tries to cheat. By proving the fact of cheating on chain, we can take away a security deposit and discourage everyone from even trying to not execute code correctly. So this is what I wanted to talk about, and I think we have a few minutes for questions, if there's any.
Any questions in the audience?
Hi, I have a question. How does the system keep up on this situation where verifiers and computational nodes are colluding? What are the measures against this?
Well, different approaches are possible, but so I believe usually it's the client whoever is paying for the execution and the verification is the one who can choose the nodes who. So if there's a big pool of potential executor and verifier nodes, that the client can pick a lot of them, at least for a random verification, and well, if any of them behaves differently, then it can hire even more. So I believe if the client is the one who is selecting the nodes, then and it is selecting enough nodes, then it's usually a good enough protection against collusion.
Any other questions? Okay, so thank you very much, Zsolt. Now we